Okay, so this is the last video for chapter 7. Okay, so, and we are going to compare the binomial distribution with the central limit theorem normal distribution, right? Because the binomial distribution can be understood as a kind of sampling distribution. So remember, in the binomial distribution assumptions, what we did is we repeat n number of binary experiments. So that is the same. We repeat experiments. So we observe n observations, right? And they are independent. That is also same. That is, so in binomial distribution satisfies identical distribution assumption and independence assumption. So identical, binary distribution with the same success probability, and independence occurs those experiments. So this is another random sampling. Binomial distribution is random sampling. But the difference is, in binomial distribution, we summarize n number of observations by the number of success, right? So instead of taking the average, in central limit theorem, we consider average of n observations, but in binomial distribution, we are counting the number of successes. Okay? In other words, in binomial distribution, we define the final single outcome as the sum, right? Do you remember? So the outcomes are so if you take a quiz, 10 questions, and each of the question is a binary outcome, correct or not, right? Correct or wrong. And the number of correct questions equals the sum of the points, right? If you are correct, you get 1 point. If you're wrong, 0 point. So sum of the points equals the number of correct questions. So you can define, mathematically, you can define the random variable obtained from binomial distribution as the sum of observations. But what we have studied in this chapter is the average, which is defined in this way. So we are studying average as summation divided by sample size n. So this is the sample average. So we learned it converges to a normal distribution. Excuse me. So that's the only difference. Binomial distribution studies the sum, but the central limit theorem studies the average. And they are also very closely related. Like, it's just whether you divide by n or not. And also, another thing I want to say here is, remember, in binary distribution chapter, I explained that the mean of a binary variable doesn't mean anything. It has no meaning. But instead, I recommended interpreting the mean as a probability, right? So also, the sample average from binary experiments can be interpreted as the percentage of success. So we are going to use this interpretation in the following example. The example is the overbooking, right? So I considered overbooking example in the binomial distribution chapter, but at the time, the number was pretty small. Like, I consider maybe 20 reservations like that, because it is not easy to think about big numbers at the time. But now we can do it, because we know we have now powerful central limit theorem, excuse me. So now I will assume that an airline accepts 400 reservations for a flight, but there are only 370 seats. And as before, the probability of cancellation is 10%, and even though I didn't say that, but cancellations are independent across reservations. Okay, so then you are selling 30 more tickets than you can afford, right? So you cannot accommodate all 40 reservations. You are overbooking 30 reservations. Now we are interested in the probability that 30 or fewer reservations are canceled, in this case you are in trouble. You are expecting there will be 30 cancellations so that you can just sell 30 additional tickets. But if it does not happen, if the cancellation is less than 30, then you are in trouble. So let's calculate that probability. First, you may use binomial distribution, right? Binomial, we can use the formula we learned in binomial distribution, or you can just simply, it's just like, you can calculate that probability on Excel. The number is too big, like 400, so it is nearly impossible to calculate by hand. So, what computer can do, so plug in n equal parameters 400 and 0.1. So we are counting number of cancellations, and the maximum number of cancellations is 400. So we plug them into the parameters, and you can calculate the probability on a calculator or Excel for y, the number of cancellations, equal to 30 or fewer. If you calculate that, you are going to get about 5.2%. So, by the way, what I want to make sure here is this is an exact probability. This is not an approximation. This is under the assumptions. If the assumptions are correct, this is the true probability, no approximation error, right? Now I'm going to compare this binomial distribution probability with central limit theorem approximation. Alternative way here, so I will calculate the same probability using central limit theorem. So what I'm going to do here is, first, probability that the number of cancellations is less than 30, you have to transform the number of cancellations into average. But we learned the relationship. So number of cancellations divided by sample size is the average, right? So we are going to divide by n for both terms, both sides, to maintain the inequality. So now the interpretation is, so originally I was interested in the number of cancellations less than 30, but now I would say the cancellation ratio is less than 0.075, right? So cancellation probability out of 400 is less than 7.5%. Then you are in trouble, right? And now what we need to do here is that now you get the probability, so you know what to do. You are going to calculate the mean and variance of this x bar, and you are going to use the central limit theorem to approximate this guy to a normal distribution, and then you are going to standardize and use standard normal distribution CDF. That is what you are going to do. Then first thing you need to do is to calculate the mean and the standard deviation of a single outcome. The single outcome here is about one reservation, which is a binary distribution. So it is pretty simple. You can apply the mean and the variance formula for binary distribution. All right. If you go back to chapter 5, we learned the mean of a binary variable equals the probability of success, which is probability of cancellation, 0.1. And the variance of a binary variable is the product of success probability and the failure probability. So here 0.1 times 0.9, so the variance is 0.09. But what's more useful is the standard deviation, which is the square root, and it gives a nice simple number, 0.3 standard deviation, right? So anyhow, in the end, for a single reservation, the mean is 0.1, standard deviation is 0.3. We are going to extend this single reservation mean and variance to the average of 400 reservations. Okay. Then the mean of 400 reservations, mean of the expectation of 400 averages, average of 400 tickets is the same, and the standard deviation of the average of 400 reservations is the standard deviation from single reservation divided by square root of sample size, which is 400. And standard square root of 400 is 20. So denominator becomes 20. So the standard deviation of the sample average is 0.015, much smaller than a single observation's standard deviation. Now you have the mean and the standard deviation of the sample average. So use them for standardization, right? So this is the probability we are calculating. Standardize x bar and the other side like this. Calculate this number. You get minus 1.6666 forever. Simply, I will approximate like this. And use Excel to find that probability. That is 4.7%. Okay? So this is normal distribution approximation. Now, compare this with binomial distribution probability. They are different. The difference is approximation error, right? So binomial distribution is correct distribution. It is calculated from the exact formula, but the normal distribution is based on approximation of central limit theorem. So this much is approximation error, and this error exists, right? But it will decrease if the sample size was larger. So as the sample size gets bigger, the probability will be smaller. So in other words, you may think like this. If you know the exact distribution, you don't need to use the central limit theorem. This is a special case where the exact probability is calculated without much difficulty. We know how to calculate that. But in many other examples, there is no way, nearly impossible, to calculate the exact probability. Then you can use the normal distribution approximation, but you have to understand that it is approximate, right? So that is another, like, this is the importance of central limit theorem. And binomial distribution is a really few special example where you can calculate the true distribution, true probability without approximation, right? And so I want you to understand the difference between true probability, true distribution, and approximation distribution. Thank you for watching. Oh, this is the end of chapter 7. And maybe I think this is maybe the midterm exam period, or if you're watching this video later, then you have done all the midterm exams. So I want you to, I hope you did well in the midterm exams. And we are, from the next chapter, what we are going to do will be much more difficult. We are going to another level, as I said, and more important, more practical. So, and take some time to review the previous chapters before you watch the next one. Okay, thank you. See you later. Bye.